Okay, we're going to go ahead and get started here in the next 30 seconds or so. We've got Ricky Beamer here for the next presentation, so if you guys want to go ahead and get settled down.
That's my last slide. There we go. Okay. So, good afternoon, ladies and gentlemen. I'm Ricky Beamer, and I have the honor to talk to you all today about the multi-purpose crew vehicle, independent verification and validation with a dynamic twist. Mr. David Ho helped me create this presentation, but he's unable to be here with us right now. So this is basically what you can expect to hear from me today. First, I'm going to introduce the multi-purpose crew vehicle and its high-level mission overview. Then I'm going to talk about SOCRRATES and PLATO and the different testing approaches we've used with these two different simulation environments. And then I'll give you some general dynamic testing conclusions and lessons learned. So MPCV, or the multi-purpose crew vehicle, is based on the Constellation program's Orion design. It will be capable of conducting regular in-space operations such as rendezvous and extravehicular activities in conjunction with payloads that are delivered by the Space Launch System, which is currently in development. And these missions are typically for missions beyond low Earth orbit. Furthermore, it will have the potential to serve as a crew backup vehicle for the International Space Station. So this is a nice overview graphic for Exploration Flight Test 1, which is set to launch about a year from now. On the left-hand side, you can see that since the Space Launch System is still in development, this test is going to be conducted using the Delta IV Heavy rocket. And we're going to be sitting there close to the top. And then on the right-hand side, you can see that we're going to do 2 orbits. The first one's fairly circular, and the second one we're going to swing around wide for a simulated deep space entry. And the purpose of this flight test is to test the heat shield and simulated deep space entry, as well as a lot of the various MPCV systems. So now we're going to get into more of the meat. So, like I said, we have 2 different simulation environments, and the first one I'm going to talk about is SOCRRATES, which stands for Software-Only Crew Exploration Vehicle Risk Reduction Analysis Test Environment Simulation, which is why it's nice to call it SOCRRATES. It was developed by Lockheed Martin for the purpose of MPCV flight software development testing, as well as verification procedure development. So, and as Justin mentioned earlier, both of our simulation environments are project developed. They've been nice enough to bring it in and get it all set up so that we can use them. So SOCRRATES has 3 main components. The first is the SOCRRATES controller, which provides our interface for script development, configuration management, as well as telemetry viewing. Then we have the flight software for the system. And then we have a component called Orion Sim, which is the vehicle dynamics models, as well as the environmental models and kind of models of the different hardware. So with SOCRRATES, there are 2 different variants. We have SOCRRATES Heavy, which is capable of running the unmodified flight software on emulated SIMX environment. And the emulated SIMX environment can be thought of as a software simulation of the vehicle management computer that will eventually be flying on the spacecraft. And then we have SOCRRATES Lite, which has its modified flight software to be able to run on ARINC 653 environment. So it doesn't have the overhead of SIMNIX, but the flight software has to be modified. So that's kind of why there are two different flavors. Like, because Socrates Lite doesn't have the overhead, it can run in faster than real-time simulations, which is great for script development. But it's not so great in that you're developing for one operating system, but then you're having to port it over into another one. So you have inherent differences and built-in utilities and some other weird things that we've discovered through utilizing it. So we're using SOCRRATES for script development and the initial debugging, and then we switch over to SOCHEAVY, which is using the unmodified flight software to be as flight-like as possible for our final script development and test execution. So here's kind of a screenshot of our SOCRRATES environment. Up in the upper left-hand corner, we just have the generic Linux terminal. In the upper right, we have the Socrates controller. And below that, we have the simulation control panel, which is our view into the kind of the real-time telemetry. Then in the bottom left, we have the SIMRINC controller, which is how the other three pieces of the pie here are interacting with the flight software. Like I said, it's modified flight software. The SIMRINC controller also gives us some access into to be able to view the sampling port information. Here is the SOCHEAVY interface, and like I said, it looks very similar. So the simulation control panel, the Socrates controller, and the terminal window are all shared. The difference is in the upper right-hand corner with the CoreSim window. And CoreSim is how those three components are then interacting with the unmodified flight software. And here's just both of them side by side. That's it. So with Socrates, our testing approach was to review the available test cases for areas that were not being tested or maybe not tested quite to the standards or the levels that we want to see them tested to. And since this is a project that's still in development, there are new tests coming out, but we don't have to stick with their schedule. And we try to, but we don't have to. And we don't have to test what they test either. So, so as part of this initial review, we've gone through, their test cases as well as the mission design data book and the fault management design document for off-nominal scenarios. We also looked into the available space shuttle anomaly data for any off-nominal scenarios that may apply to MPCV. We cross-reference this data with the fault management design document and the mission design data book for any possible commonalities. So here's a pictorial representation just kind of showing there at the bottom on both sides for these two different paths. So we start off with a lot of data, kind of applied some filters, and then we ended up with our MPCV independent test cases. So with the independent test cases that came out of the prior survey, we developed high-level pseudocode and procedures that we then used to translate into the Socrates Common Control Language, or CCL, which is the common scripting language between Socrates Lite, Socrates Heavy, and even their hardware on the loop simulators. And so this involved extracting proper commands and telemetry information from the data and command dictionary. Let's see, and through this process, I've mentioned a lot of this already, but we've been able to develop our own procedures and test different scenarios or test the same scenario in a different way to validate the flight software behavior in nominal and off-nominal situations. And we've been able to provide more concrete assurance for other analytical work. So now I'm going to get to walk you through an example of a SOCRRATES test case. So let's say that we want to know how the flight software behaves during scenarios where we have invalid launch vehicles. The discrete values are basically a set of zeros and ones that function in kind of a known pattern in accepted order. So before something happens, these will change to basically as a check mark to say, yes, everything's ready on this end. Let's proceed to the next step. And so let's say that for our example mission that these discretes indicate that a segment transition is ready to occur. And the segments are basically, you're sitting on the launch pad is one segment. During power descent, you're in another segment. When you're in orbit, that's another segment. So these different discretes will change just prior to these transitions. So what we want to look at is what happens if an invalid set of discrete values is encountered. So we assume that the flight software would not allow the transition to occur, but we didn't know this for certain. We referenced the flight management design book, or the fault management design book, and the mission design data book, and to come up with some of these assumptions. And so basically that's what we did. We ran several different tests under nominal situations, just observing, see, did the discrete values change in the way that these other documents said that they were going to change in? Did they happen at the time that they said they were going to happen? And then we went through and did some off-nominal testing where just before the segment transition was to occur, we injected bad values. So, instead of 0, 1, 0, we put in all ones or all zeros. We just changed it and observed what happened. And what we saw is that the flight software didn't transition. It didn't meet that check, and it stayed in the segment that it was in. So some of the challenges that we've encountered with SOCRRATES is that the test scripts aren't guaranteed to work across multiple flight software builds. This is due to the dynamic nature of the command and telemetry GUIs. And this has made regression testing very difficult and time consuming because now we have to go back and edit our previous scripts to the new values that are being used for that software build. So that's made our pre and post test analysis a bit more complex. Additionally, as with a lot of testing environments, there's a good bit of a learning curve involved in order to be able to utilize the simulation software to its full potential. And now we'll move on to PLATO. So PLATO stands for Partition Level Application Test for Orion. And is a software execution environment that allows users to interact with the Orion flight software partitions at their sampling port boundaries. PLATO also runs unmodified flight software, which is again key, as Justin pointed out earlier. PLATO provides displays and scripting facilities for automated and ad hoc testing, and it was developed by NASA ER6 at the Johnson Space Center. And then just to establish some common definitions, the partitions are the individual parts of the flight software, and sampling ports are communication objects that allow flight software partitions to generate command statuses and responses for an aviation or space vehicle. So again, similar to SOCRRATES, PLATO executes unmodified flight software on an emulated SIMX target. One of the big advantages to PLATO that SOCRRATES does not currently have is that it allows us to step through the flight software minor frame by minor frame and with that, we're able to control with very fine detail the data flow from one partition through the different paths to the other partitions. Furthermore, testing at the partition level allows for the evaluation of each individual partition interface, as well as it gives us the ability to isolate partitions and do a little more black box testing on them. So this is a screenshot of the PLATO interface. On the right hand side, you can see that it runs in any modern web browser. And then because we have all of this on a common virtual machine, we're able to see some of the other background information. So the scripting language for PLATO is Python. So in the upper right hand corner, you can see a Python terminal window. And then TTNet, Homer, and the SEMIS control panels are all there as well. And those are more for the back end information, but useful for certain types of debugging. So with PLATO, we took a little bit of a different approach to our test case identification. Within the MPCV program, there are various documents that describe system design patterns that are used or that were used during the software development. And so these are called technical memorandums, or I'm going to refer to them as tech memos. So we read through these and we had to apply several different filters when we were doing this. First and foremost, what sticks out? Do these documents make any definitive claims that this is how the software was being developed? Why is it being developed that way? Can we go through there and test, is that truly what they held, is that how they really designed the software to meet this pattern? Another thing is what would make for an interesting test. Like with dynamic testing, you can generate scenarios until you're old and gray, but not all of them are going to be useful. I mean, they're all useful, but they may not contain information that's really relevant to anything else. So we had to see what would make an interesting test and kind of why should we do it. Another filter we had to apply was what can be tested in PLATO. So PLATO is a very capable system, but every test simulation system has its limits. And so we had to make sure that our test met those, or were within those limits. And finally, something else I personally like to ask a lot is, what are the human factors involved in that software? So in the end, the software is always a long string of zeros and ones. But at some point in time, somebody somewhere had to plug in the algorithm and either generated the ones and zeros or plugged in the algorithm that became the flight software. So is there anything within the tech memo that we looked through that we could test kind of the human factor of it? So this helps scope our investigation, but then we had to focus it down a bit more. So we, again, asked additional questions. So one is like for each test case that came out of the last investigation, what are the guiding ideas or what is the purpose behind that test case? Why or what is important about it? And why should IDEB care about it? And then are there any concerns or blockages that we need to either work around or mitigate, or are they going to prevent that test case from being executed? Here's my PLATO example, and I want to stick with kind of the segment transitions. So let's just say that the flight software is driven by events, and the events kind of trigger the segments. So throughout the mission profile, we have X number of events, and every segment has some number of corresponding events assigned to it. And it's somewhere between 1 and all of them minus however many segments there are. And so these events are like, once the software has detected the event, it will trigger a flag, basically the flight software at all times can see every event throughout the whole mission, but only they should only be paying attention to the events that are in the segment that's currently in. So, it can see everything, but it's only focusing in on one area. And so that's basically what we tested. We went through and we tried to, we set the event triggers for every event not in that segment first to make sure that it didn't transition. And then we went through and set the events in that particular segment. And once the last one was set, it's supposed to say, hey, there's a transition ready, and then transition. And on that transition, it goes through and it clears all the event flags. And when we implemented this in the script, that's exactly what we saw. We triggered every other event. It didn't transition. Then we triggered the events in that segment. It said, yes, there's transition ready, and then it stepped on through and cleared everything out. So kind of some of our challenges with PLATO is, again, there's a steep learning curve. Another big challenge is that the scripting API used is very command line driven. And we have to use the scripting API in order to interact with the flight software at the level that we're trying to get to. Because it's command line driven, I mean, I'm a little bit clumsy when it comes to typing, so a 5 can become a 6. And then the script will execute just fine, but I may not get the results I'm looking for because now it's doing something different. So it's a little cumbersome and slow to go through and see, okay, my test executed, it didn't do what I thought it was going to do, now why? Oh, because on line 200 of a 1,000-line script, I have a 5 instead of a 6. And that kind of leads into my last bullet, which is it's easy to create non-flight-like scenarios. There are different data load processes that happen well ahead of where we're intersecting flight software. And so, like I said, what it says in here is that sampling ports are bound by data type, not by the upper and lower bounds, which is handled somewhere else. So there are a couple different test cases that I went through where I didn't understand initially what I was getting in the end because I was creating a non-flight-like scenario that took a lot of debugging to figure out what was going on. So here, we just have to know a little bit more about what to expect from the flight software instead of like true black box testing. So now we'll get to just some overall dynamic testing conclusions. We've been able to provide the capability to design and develop different test scenarios within the IV&V program. And we've developed some of these tests in parallel with the program. A lot of them we've developed separate from them. And it's just given us another tool in our bag to be able to go to the program and say either yes, the flight software, we have good confidence that the software will do what it's stated to do, or we can take our issues to them and say, this is what's happening. We've traced it down and it's in the executed code that's going on. And then we've also been able to provide more concrete evidence for our traditional analytical results. And that has also helped us better scope our severity drivers and provide more concrete evidence as a whole. Here are just some general lessons learned. I'm an introvert by nature, so I had to basically step out of my box and ask a lot of questions to a lot of people to keep investigating all the way down until we finally came to some agreeable solution for different issues I've encountered. Through the whole thing, I also had to learn how to document properly so that I can follow my train of thought 2 months later, 5 months later, or hand it off to somebody else. And with that, I am done. So, any questions?
Any questions?
A lot of it was we were looking at very specific documents. Like so with I know with PLATO because that was where I was more involved. There are very specific documents that we looked at, and we scoped our analysis to just those documents. We're still going back through and rereading them, seeing other areas where we can test again. And then some of it was also kind of schedule driven. Like we had to we had to figure out how many tests we could realistically deliver by a certain time frame in order for it to be kind of incorporated and accepted back into the big project. So some of it was driven that way. A lot of it is, at that point in time, and even now we're still learning a lot about it. So we're trying to see what can we do right now. What will kind of push our bounds just a little bit so that we can learn a little bit more. With the SOCRRATES area, there's a lot of testing that we still need to do in that realm. There's a lot of work that's been done that we need to follow through on. So it's we did a little bit, and we also looked at our internal risk to see where we can either mitigate or investigate them a little better. Which those will be, your more high severity areas. So those did play into it a little bit. So the CCL scripts, that is, I believe it's a commercial product, but we're using a very script out, very narrow set of commands from it. And then with the PLATO area, we're using Python, which is a widely available language, but there are custom commands that have been used. And so kind of an example of the difference is that in SOCRRATES, there's a GUI that allows you to select, I want to test this, or I want to generate this command that affects this area. Whereas in PLATO, we go to the data and command dictionary, and we have to supply in the hex values or the decimal values for everything in the payload that's being transmitted with that pattern. So that's where there's just a little bit, like I had a couple different typos when I was trying to execute it. It just didn't work the way I thought it was. But it still ran like it, because it still does work. It's just the command's not right. Right, yeah, we have to figure out what we can do with the time we have.
Okay, if anybody has any other questions, we'll have Ricky in the breakout session over in the next room, just down the hall to the right, or online. You can connect online there, or dial into the telecon. So we're going to move on to the next presentation.